Sydney here. So we will talk about multisections of manifolds.
Well, thank you very much for the kind invitation. It's a pleasure to be here. So, when I was told I could speak about whatever I want, and it can be a related topic to hyperbolic geometry, I thought I'd like to talk about multi-sections, because somehow I haven't talked about it much. And so most of what I talk about is either work by Gay and Rob Kirby, or joint work with Hyam Rubinstein. And there are two papers on the archive that contain most of the material. And then there's also some other material that is fun to look at. So there are two papers by Jeff Meyer and Alex Zupan, and then one by Maya Sherma Zupan, where they have applications. Okay? And another thing I want to advertise is, Dave, Rob, and I think Alex are organizing a workshop at the American Institute of Mathematics, which runs next year in 2017. And as you probably know, I mean, the AIM workshops, anyone can apply to participate, and they're especially keen for young people to come and work on things. And so this is, multisections is something, or trisections is something that's reasonably new, and it's a field that's sort of still developing, and we're really wondering what is a good way of making use of it. Yeah? So just as Heegard splittings were maybe completely useless when they were first invented, because they just apply to any three manifold is Heegard splitting, so how useful can it be? Yeah? Similarly, multisections or trisections can apply to any field manifold. But what people are sort of looking for, or we are looking for, is sort of the equivalent of sort of a Casson-Gordon theory that really revolutionized the theory of Heegard splittings. And so those are kind of tools that are missing. And one other thing that is of interest is, of course, the focus on interesting families of examples where maybe one can do things. But so maybe some of these comments become clearer in these talks. So my plan for today, I sort of have a sort of a wish list of what I would like to talk about. So it probably goes up to here today. So to recall, Heegard splittings gives a motivational example, CPN. Then talk about four manifolds for the rest of today. And then if you haven't had enough of multisections, then I will carry on Wednesday and talk sort of about one way of now thinking of the structure, or the theory of finally presented groups being really equivalent to the study of smooth four manifolds and multisections in arbitrary dimensions, and then also some sort of nice applications here, realizing non-positively curved tubings in all dimensions. And I had two more points, but I didn't fit on that board, so I didn't put them there. So I will also talk about other constructions of multisections and open problems. We have a lot of open problems here. Okay, so let me start with the first point, Heegard splittings of three manifolds. So let me just draw two three-dimensional one-handlebodies. Here they are. And maybe this one here, I just draw sort of the some one handles in here, and here maybe as well. Like so, yeah. So these are my handlebodies, and they're really nice, solid objects. And Heegard splitting is just anything of this form where you take these two handlebodies and you just identify them by a diffeomorphism of their boundaries. And so to denote them H0 and H1, I get the three manifold is just the union of H0 and H1. H1 identified along using phi. And so this picture comes naturally with a height function. Of my three manifold to, in this case, really the one simplex. Like so. Yeah, where the pre-image here is this red graph. The pre-image here is this blue graph, and every point in between has pre-image genus 2 surface. Yeah, so the pre-image of every point here is a genus 2 surface, and here see this graph is a pre-image, and here see this graph is a pre-image. Yeah. Okay, and also, I mean, the other thing that one sees, of course, then from this kind of picture, if one thinks about the generalized Van Kampen theorem, it gives the pi 1 as a push out. So here we have the fundamental group of a closed surface of genus G, and then it surjects, of course, the fundamental group of this handle body, and it surjects the fundamental group of this handle body, and these are both just free groups. Yeah? Okay, so we naturally get this push out. Okay, so this picture is really what we want to generalize. We want to generalize this to any dimension. Let me just briefly say on the existence proofs, of course, of Hilbert splittings.
So H0, H1 is a two-dimensional.
I beg your pardon?
H0, H1 is two-dimensional.
These are three-dimensional. Yeah, so these are the solid handle bodies.
Solid.
Yeah, so solid handle bodies. So maybe if I indicate this like this here with the this shaded. Yeah. Yeah. So I mean, in this picture here, you can think of them as really just neighborhoods of these graphs. Yeah. You have these two graphs, and you just take the neighborhoods in R3 if you wish. Yeah. And then you identify the boundaries via your favorite diffeomorphism. Okay. So existence proofs. So there are two classical existence proofs. I mean, one can guess already from this picture here. One really comes from just Morse theory. Yeah? Yes, in the theory of Morse functions, I guess what you can think about is if you have a Morse function of a compact manifold, of course you're going to see a minimum and a maximum somewhere. Yeah? And these give you 0 handles and 3 handles. And any other 0 or 3 handle that you might see, you can just cancel with 1 and 2 handles in between. Yeah? So you can really arrange for a Morse function with just a 0 handle, a 3 handle, and then lots of 1 and 2 handles. And again, you can do handle slides to arrange all the 2 handles to sit above the 1 handles. Yeah? So that's how you see the 2 handle bodies. Then one really having here the 0 handles and the 1 handles coming from the critical points of index 1. And here you have a 3 handle, and then all the other 2 handles, yeah, coming from the critical points of index 2. Okay, so this is how you can use Morse theory to prove the existence. And the second proof is combinatorial. And this is somewhat the classical proof, and whilst maybe it doesn't look quite as elegant as the Morse theoretic proof, this is the one that we will generalize, because it's also sort of the combinatorial approach is really what helps us also to compute things. Okay, so let me just remember or recall the combinatorial proof, because this is what we'll be working with. So you start with a triangulation. Yeah, so here K is a simplicial complex, yeah, and this here is the topological realization of my simplicial complex, and I assume that I have this homeomorphism, yeah, homeomorphism from the topological realization to M, and so this is what I think of as a triangulation. Okay, and then we take the first pericentric subdivision. That's often denoted using a prime, so this is K prime, and so let me draw simplex, let me draw sort of the pericentric subdivision. will not draw it on the back, but let me just draw the barycenter as well, and just focus on what I see here. Yeah. So then any simplex really up to symmetry looks like this dude here. Yeah, where I see one vertex coming from the 0 skeleton, one vertex coming from the 2 skeleton, one from the 1 skeleton, one from the 3 skeleton. Yeah? Okay. And so what one can now do is one can now partition the vertices. And let me maybe take this guy out and put him here. Yeah, so here my labels 0, 2, 1, and 3, depending on what skeleton they come from. So I can just take the graph, say gamma 1, graph spanned by these kind of vertices in the interior of 0 or 1 simplices. The original triangulation, and gamma 2 being the graph spanned by vertices in the interior of the 2 or 3 simplices. Yeah, so then you see that gamma 1 is really just the original 1 skeleton of my triangulation. So gamma 1 is just going to be here, the original 1 skeleton. So 1 skeleton. Okay, and this here is really what is called the dual 1 skeleton. Yeah, so the vertices are just barycenters of the tetrahedra, and then they just sort of bounce through the interiors of edges. Yeah, so let me draw it like this here on the side. Yeah, so this is what this one looks like with these guys sitting here, here, and then down there, and then up here. Yeah, so this is the dual 1 skeleton. And so in particular, both of these graphs are connected. Yeah, so gamma 1 and gamma 2 are connected. And if you look at these graphs and you sort of can naturally thicken them up, of course you can make this precise using the second barycentric subdivision. Yeah, you really see that here 3 manifold is now just a neighborhood of the one graph union a neighborhood of the other graph, and they meet along their boundaries. Yeah, and so in particular, if you think of how they meet these tetrahedra, so each of these graphs meets each tetrahedron in a pair of opposite vertices. Yeah, and you get a natural simplicial map actually to the interval. Like so, yeah. So this is your natural simplicial map, yeah, where you really just then pull back from this vertex, this graph gamma 1, from this vertex, the graph gamma 2, yeah. And now if you look at what you get from, say, any point on the edge, you naturally see these very nice quadrilaterals, and they look like normal quadrilaterals in these tetrahedra, yeah. And this pulls back your Hegat surface. Okay, and so then one thing that I also quickly then want to say here is that if you look at this where am I looking? So if you now think about the degrees that you have here around these vertices, so my quadrilateral, so it doesn't meet 0, 1, it doesn't meet 0, 2, so it has vertex here, so on this edge here, the degree is actually 4, and on the 0, 3 edge, the degree is going to be 6, 0, 3. 6, and then along the other ones, it's going to be 4 again. Yeah. So if you then look at the cubing that you get, right, your surface comes with a natural cubing, and this cubing is actually non-positively curved. Okay. So this is actually the surface as a non-positively. Yeah, so in particular with this kind of, and actually it's because of the 6 here, you can even say it's a negatively curved cubing, right? Yeah, you're going to get something with negative curvature. So in particular, the simplest Hegat splitting that you can think of, like of S3 with just a 2-sphere, you're not going to get with this method here. Yeah, but you can get all sorts of other interesting cubings of surfaces. Okay, and so this is also one aspect that I want to generalize to higher dimensions, where so this will become much harder to achieve, because here, of course, all we just care about is sort of the degree of the vertex, but in higher dimensions we need to worry about Grommer's link condition. Okay, so then just another sort of thing to
excuse me?
Yeah?
What is the definition of cubing?
So cubing is in this case just say a CW complex that's just made up out of cubes.
Okay.
Yeah, so 1-dimensional, 2-dimensional, 3-dimensional, and so forth cubes, and they don't all need to be of the same dimension. But in this case, they're all 2-dimensional cubes. Mm-hmm. Okay, and so then the other thing we have is we have the Reidemeister-Singer theorem. So, which says that if you look at any 2 Hegat splittings of the same manifold, then you can actually stabilize them so that they become isotopic. So, any 2 Hegat splittings of M, let's say it this way, have a common stabilization. So what is the stabilization? So let's look at this locally. So here's my surface sigma, and here's my handle body H0, here's my handle body H1. Yeah? So now what I want to do is I want to increase the genus. Yeah? And I could of course just take any old arc starting at H0 and going out here, and then coming back here to sigma. Yeah? Okay? So you can take this arc and then you can drill it out and think of this as attaching a one handle, yeah? A one handle to H0, yeah? Of course this drills out a one handle of H1, so think of this as attaching really a 2 handle, yeah? Here you see a 2 handle that if attached to H1. And you've also increased the genus of sigma. Yeah, so this increases the genus of the Hegat splitting. Yeah, so if you want to think about it in this picture here, you can think of this as sort of a little worm has just sort of eaten a hole into this handle body here. Yeah, but taken whatever it's taken out here and actually stuck it on here. Yeah, so this is the stabilization procedure. Okay. And the only thing you need to worry about is that you don't choose an arc that is knotted. So we're only able to draw a knot, right? Let's do this first. Let's first draw a knot and then sort of just put it here. Yeah, so if you did something like this here, yeah, then of course the result after doing this, I mean H0 is going to be a handle body, that's fine, yeah? But H1 is most likely not a handle body. Yeah? Okay, so you do not want to take a knotted arc. We want to take an arc that basically is nicely isotopic into your splitting surface. Yeah? Okay, and so this amazing theorem, what it says is that you give me any two Hilbert splittings of a manifold, I can just drill tunnels, yeah, into each of them, stabilize them, and then these stabilized things are actually isotopic to each other. Yeah, so that's what Reidemeister-Singer does. And again, if you think about proofs, and I will not give either of them. So one again uses Morse theory, or really surf theory. Yeah, so what you do is, I explained before, you can think of a Hilbert splitting as maybe dual to a Morse function. Yeah, you have your two Morse functions, and you basically want to build a homotopy between these Morse functions through other Morse functions, and you can arrange this so that really all the critical points of index 2 stay up here, and the critical points of index 1 stay down here. Yeah, and then topologically you can realize this as just a sequence of really these kind of stabilizations. Okay, so this is, and the classical proof is combinatorial. Okay, but I will not give this proof because it's just going to be irrelevant for what we do. Okay, and so often one can actually find splitting. Here I said, well, take any triangulation and then take the first pericentric subdivision. You end up with a whole bunch of tetrahedra and more than you usually need. Yeah, so often can find splittings, yeah, Hilbert splittings using more efficient triangulations. Really all you need is, right, all you need here is these two graphs. Yeah, you need to somehow find two graphs in the one skeleton with the property that they meet each tetrahedron like this. Yeah, each tetrahedron just meet it in a pair of opposite edges. Plus, you want that these graphs are connected. Yeah, you do not want them in the end to be, say, the red graph to be disconnected or something. Yeah, so all you need is a partition. So find more efficient. So I need to identify partitions. With the desired properties. Yeah, so as an example, if you think about the standard triangulations, two vertex triangulations of length spaces, so if you think about LPQ, right, so how do you get LPQ? Well, you take some kind of p-gon. So let's draw maybe L52. Yeah? You take a p-gon, you take the suspension of that. Yeah, you do this. And now we just identify, and we triangulate this by just putting an edge in the middle, right down the middle. Edge right down the middle. And now what you do is you just identify, say, this triangle on top with, what do? You turn by 2 pi times 2 and 5, so 2 and 5 twist, right? You turn this and then you basically reflect it down. Yeah? So this is how this face is identified to, say, this face here. Okay? You just take it, move it 2 notches along and then reflect, and that's the way it's identified. Okay, so here you just really turn by, so you do a 2 and 5 turn. And what happens in doing this is then, say, this edge here is identified with 2 along this edge here, identified with 2 along this edge here, 2 along this edge here, 2 along this edge here. So you see that all of these edges along here are identified, and what you also get is that this edge here is, of course, just a central edge. Yeah? Okay, and every tetrahedron now looks exactly the right way. It has sort of this red edge here and a blue edge here facing it. Yeah? So you have these two edges facing each other. And this is exactly the standard sort of Hilbert splitting with a torus as the Hilbert surface. Yeah? So this gives you a standard Hilbert splitting of a length space. here, because here everything will have negative Euler characteristic. Or just to give an even better example, you can do even better sometimes. I mean, if you think about the one tetrahedron triangulation of S1, you can do it like this. So this is a singular triangulation now. And what you do is you take this one tetrahedron, you identify these two faces, like so, and the back faces, like so. Yeah? So this is actually one tetrahedron triangulation of S3. And again, you see the Heger torus in here very nicely. Yeah? So this is your Heger torus. This is identified with this, and this is identified with this. Yeah? By the back faces. Okay, so somehow there are better ways of doing things. Okay, so again, this is just motivation. I mean, this is something one might like to do in higher dimensions. Okay, so much for the motivation of what we want to think about and generalize. Any questions? Or is this all too familiar? Okay. So anyway, so let's talk about the tropical picture of CPN. Yeah, so here is, I guess this thing is called the moment map here. So you have this map from CPN to the n-simplex. Like so. And how is it defined? Well, you just take a point and you map it to, well, take 1 over the sum of the moduli and then times the moduli here. Like so, yeah? Okay, so this is a map from CPN to the n-simplex. So for instance, if n is equal to 2, so CP2 is mapped to a simplex here. And then we should ask, who has thought about this map before? No one? Okay. So excellent. So what's the preimage of this point here? I mean, the vertex 1, 0, 0. Say, what's the preimage of this point here? In CP2. 1 point. Yeah. Yeah. So preimage is 1 point. So phi inverse of, and that's actually true for each vertex, right? Phi inverse of vertex is the point. What's the preimage of, say, taking a point here somewhere? Circle, yeah. Yeah. So here we have a circle sitting above this, and that's true actually for every point here on an edge, right? You're going to get a circle, and what you get if you look at the preimage of, say, a point in the interior. Yeah, so you get a 2 torus. Yeah, so this here actually gives you a 2 torus. Okay. Yeah, and so now if you look at this kind of picture, and this is a 4 manifold, right? And I said we want to sort of trisect 4 manifolds in the end. And what do you get here? I mean, if you think about these points, actually, these points kind of, you can grow them into balls. Yeah, and you grow them into balls maybe until you hit these bits here. Yeah. Okay. So you can grow these here into balls. So really, you have 3 balls here. Yeah. So you decompose CP2 into 3 4-dimensional balls. That's the preimages of these natural cubes you have here. Okay. And so what's the intersection of 2 of these balls? Well, here you actually see. I mean, here you have this torus, and let's maybe draw this torus. Here's my torus. Yeah. And as you sort of think about this torus, what happens as you go here to the boundary? Well, in the boundary you just have a circle, right? There's a core circle here, and there's another circle associated to this collapse as you collapse here, right? And there's a circle here where the radius of the circle just goes to 0. Yeah? So you can really think of this as associated to this here, curves. I mean, you have two curves, and these are generators for your torus. And you have one curve that survives, and you have another curve that's associated to the collapse. Yeah? And in fact, the way I've drawn it is here, along here, this here is really isotopic then to the core curve. Yeah? And this here bounds this kind of disk. Yeah? So as you do this here, I mean, the preimage of this bit here, actually, the preimage of this here, of this whole sort of segment here, the preimage then is a solid torus. Okay? By symmetry, of course, the same thing is true here. Here you also get a solid torus. Yeah? So you've really subdivided the boundary of this 4-ball. So think of this as a 4-ball in CP2. The boundary is a 3-sphere, and you subdivided it into a solid torus union along a torus and again a solid torus. So this is actually a Higgs splitting. Yeah? So you actually have a Higgs splitting of the boundary of this 2-sphere here. Yeah? And this is a symmetric picture. Yeah? So this picture is symmetric, and in fact, to each of these collapses, you can associate curves. I mean, you can choose coordinates if you wish, so that one curve is the 1-0 curve, one is the 0-1 curve, and the last one is the 1-1 curve. Yeah? And you can make all of this very explicit by just working out what this function is and choosing coordinates. Yeah? So this is what you get. And another way of maybe seeing this nicely is, I mean, people in tropical geometry wouldn't draw this. People in tropical geometry would draw this here, right? And then they would draw this here. And this is exactly where you see these slopes here. You see the 1-1 slope, in this case the -1-0 slope, and the 0-1 slope. Yeah? Okay? But these are really then related to these slopes here. Okay. So so this is this picture that we have from CP2. So let me maybe summarize some of the key features. So if we think about CP2, we've now subdivided it. So this is somehow CP2. And I'm mapping it to the, I should have drawn it more as a dual picture then. So let's try again. So here's my simplex. The simplex has from this dual spine here, and this dual spine is denoted pi2 inside delta 2. Yeah, so we have this dual spine in here, and this gives the simplex a cubical structure. Each of these cubes here pulls back to a ball, so you have a ball, maybe B0, here B1, here B2, from the vertices 0, 1, and 2 here. And then this intersection here is a solid torus, and this here is again a solid torus. Solid torus. And this here is just a torus. Yeah? Okay. And you also have this diagram really that goes with this thing that tells you actually how to build CP2, right? And this diagram really just tells you, I mean, take this guy and which way I have the colors here, but here's one curve, yeah? This is one curve along which you sort of glue in, yeah, to get this. One curve that you glue in to get this, and then these together actually give you the Higgs splitting for the boundary sphere here, and you have the third curve giving you the third splitting. Yeah, so this is really, think of this, Gay and Kirby called this here a trisection diagram. Just as if you just omit one of the curves, it's a Higgs diagram, yeah, for the associated 3 manifold. Okay. Okay, but so this is basically the general thing that we want to generalize, and then also thinking about this in higher dimensions. Right, in higher dimensions, it's a similar picture. If you think about what you pull back from a vertex, Yeah, from a vertex you pull back a point, and then you grow it, yeah, into a ball. And again, you just think about the sort of dual pictures here. So these dual skeleta, yeah. So in a tetrahedron, then it's exactly this kind of butterfly picture, like so. Yeah, it's this butterfly picture here where, again, at the vertex here you see a cube. Yeah, so here you see 3 faces of the cube meeting at this vertex. Yeah, and then the other 3 faces on the back. Yeah, so you see these cubes, and then the double intersection of 2 of these again is a cube, and the triple intersection again is a cube. Yeah, and then the quadruple intersection is just this point, which is the 0 cube. Yeah, so you have a very nice sort of cubical structure here. And this is what we pull back to the N manifold. Yeah. Okay. Let's see. So then, guess I'm ready to move on to the work of Gay and Kirby. About trisections. So let me actually simplify and generalize their definition. So simplified / generalized. So trisection of M collections of submanifolds. And so anytime I mumble manifold or submanifolds, just think piecewise linear. Yeah? So of course in dimension 4, you can also think smooth, but then in higher dimensions, not anymore. So of 3 submanifolds, H0, H1, H2, such that, so the first thing is that each H of k is equivalent with a standard four-dimensional one-handle body second condition is that I want all the interiors to be pairwise disjoint, just as in this picture. So interior of Hi intersect interior of Hj is empty, and I want that my manifold is the union of all of these. And then the next thing that I want, just as here, I want the intersection of any 2 of them to be a 3-dimensional one-handle body. So Hi intersect Hj is a standard 3-dimensional one-handle body. Yeah, again for all combinations of I and J. And the last condition is that the triple intersection is a surface, a closed surface. Okay. Yeah, so this is the definition, so let's make some observations that then take us to the way Gay and Kirby think about this. I mean, so what do I have when I think about this four-dimensional? I mean, what's a boundary, right? What's a boundary of a four-dimensional one-handle body? Yeah. So if I think about this one-handle body, I mean, here's my 0 handle. Yeah? And then I attach all these one handles to it. Yeah, so let's just draw this schematically. Yeah, so what I attach here are a whole bunch of V1 times V3s. Yeah, and so what's the boundary then of this? Well, what do you get when you just do one, right? So forget about this guy. What do you get as the boundary of this here? Sorry?
Is it cylindrical?
I mean, it's going to be a 3-manifold, right? Yeah, so this is a 4-manifold, so the boundary will be a 3-manifold.
S2 cross S1?
S2 cross S1, yeah? So if you do one of them, it's S2 cross S1. And so then if you do a bunch of them, it's a connect sum of S2 cross S1, yeah? So this here has boundary in this case, let me write it, so it's 1 cross S2, and then connect sum 3 times, yeah? In this case. I mean, I've drawn it with 3, so I'm writing a 3 here, and generally you have K, and then you have a K here, okay? And so now the S2 cross S1, so now we need to think about Hegel splittings again. So Hegel splitting of S1 times S2. Well, how can you get one? Well, you just think of this here as S1 times D2, right? Union S1 times D2. And there's your Hegel splitting, yeah? Okay, so you have a genus 1 Hegel splitting, and there's actually just one, yeah? Up to homeomorphism, there's just one Hegel splitting, okay? And it turns out that here, so this is genus 1, and this here actually the minimal Hegel splitting is genus 3, and you just connect some all of these, yeah? So once you have a Hegel splitting, of course, you connect some Hegel splittings by just, doing, I mean, what's a connect sum, right? I mean, you have 2 manifolds, you take out a ball here, you take out a ball here, and then you identify, yeah, along the boundaries, right? That's a connect sum. And so if you have a Hegel splitting, just choose your ball to go through the Hegel splitting in a standard way, so that this here looks like a disk in a ball, this here looks like a disk in a ball, and this means you can actually then also glue up the Hegel splittings here to give you a Hegel splitting of the connect sum. Okay, so this is this. So this here has a minimal Hegel splitting, in this case of genus 3. And then you can stabilize, okay? Hegel splittings can be stabilized. And now there's a wonderful result due to Haken and Waldhausen that actually says that any 2 Hegel splittings of the same genus are actually already equivalent. You do not need to stabilize. You don't need Reidemeister, Singer theorem, and go up, yeah? Any 2 Hegel splittings of this guy are actually isotopic. And so, so this means all Hegel splittings of this connect sum are standard. So Haken and Waldhausen tell you that any 2 Hegel splittings of connect sum of K is 1 times S2 of the same genus. So let's put it this way, any 2 Hegel splittings of genus G, yeah, of this guy have G greater than or equal to K and are isotopic. Okay, so there's just a unique way to do Hegel splittings of these manifolds. Okay. So the picture then that we have here in this setup is right. So what do we have from a trisection? We have a decomposition of our manifold into something that is a handlebody here, a handlebody here, a handlebody here. Yeah. Okay. Then the triple intersection is some kind of surface sigma. And here again you see a handle body. In this case a three-dimensional handle body. Here you see a handle body. And here you see a handle body. Yeah? So this means that the boundary of this guy, and the boundary of this guy is just to connect some of S2 cross S1s. Yeah? And it comes with a Hilbert splitting. Yeah? Comes naturally with a Hilbert splitting. Here's a splitting surface. It divides the boundary into two handle bodies. Yeah? And then you actually know this is the standard Hilbert splitting of whatever genus the surface has. Yeah? So this is a surface of genus G. So and the genus of then sigma must of course be greater or equal to the genus of HK for each K, yeah, by what Hagen and Walthausen tell us. Yeah? Okay, so that's the first observation. And then, so that's the first thing that sort of, if you look at Gay and Kirby's theorem, what they want you to know here is that this here is basically the standard Hilbert splitting that you see here of the boundary. And then the second thing that they actually want is they want the genera of all of these three here to be the same. Yeah? At the moment we do not know that they're the same, they could be different. Yeah? I mean in our example here, they happen to be the same, I mean they're all balls. Yeah? But in general they don't need to be the same genus by the way I've written it down here. Yeah? And you can actually build multisections, trisections where they have different genera. Okay, so they want them to be the same just so that it's like Hilbert splittings, because in a Hilbert splitting it's automatic that they have to have the same genus, yeah, because they share this genus G surface in their boundary. So here it's not necessarily the same, but we can arrange for this actually. So, so claim can arrange, if we like, yeah, for all HK to have the same genus. And so in order to show this, what it, yeah?
I have a question. In your definition, there is no connectedness assumption. Is because it is the products or?
Each of them, each HK is a standard four-dimensional handle body.
No,
so that's
the intersection.
And the intersection again is a standard three-dimensional handle body, so it is connected. Yeah. Mm-hmm. Yeah. So that's you get a ball, and you can do it all with a two-sphere. Yeah. So you have a two-sphere here, bounding then, yeah, a ball here, and ball here. Okay. So you have these three trisections, all using just balls, okay? But then they're distinguished by the way their intersections fall here, okay? These are all trisections in the sense of Gay and Kirby because they all have the same genera everywhere. Yeah? Okay. Anyway, so this is the last thing I think I'm going to do with balls. Okay. And one thing I should say is, so from this you can concoct now invariants, of course, of four manifolds. Yeah. So a new invariant would be this kind of trisection genus, which is really not. So it would be a triple of numbers, right? And you have the genera of the handle bodies, but then you also take genera of the pairwise intersections, and you take the genus of the triple intersection. Yeah. Yeah. So the multisection or the trisection invariant is in this case a 7-tuple. Of numbers, yeah, that you lug around, and I don't know whether there's an algorithm to actually compute it. Yeah, yeah, but I guess computing Hilbert genus is also not easy. Okay. So what I want to do next is then I want to give the existence proof in dimension 4. So this uses triangulations, and so it will again not not actually give you these kind of nice and simple trisections that involve chords. It will be slightly more complicated stuff. Okay. Okay, so the existence proofs. So we start with, again, a triangulation. And we again take the first barycentric subdivision. And again, we concoct these graphs by just looking at where vertices sit, yeah, on which skeleton they sit. Okay, so gamma 0, the graph spanned by the vertices on interiors of 0 and 1 simplices. Then gamma 1 is graph spanned by vertices on the interior of 2 or 3 simplices. And gamma 2 is a graph spanned by, well, no, we just have 4 simplices left. Okay. So you probably sense a problem here. Yeah, so the if you look at gamma 1, yeah, gamma 1 is a happily I mean, if you look at any four simplex, these things are also called pentachora. So here's maybe my Mickey Mouse picture of a 4 simplex, yeah. So then the vertices lie either on, I mean, the vertices really are just labeled like this, 0, 1, 2, 3, 4, yeah. Just how they fall here with the barycentric subdivision. And so again, if I look at these graphs, I mean here, this graph meets every 4 simplex in an edge. This graph here does as well. But the last guy does not, right? The last guy just gives me isolated vertices. Yeah. And because this here really gives me, and this graph here really gives me the one skeleton, yeah, this is connected. This here is also not hard to see that it is connected. Yeah, just go via the dual. And this one here is just as it is, a bunch of isolated vertices. Yeah? So we need to basically rectify this situation here. Okay, the isolated vertices. So this is connected. And this is isolated vertices. Okay. And so the way to do this is to notice that, of course, here, if you look at any pentachoron, it has a unique 3-phase that has just the other 2 colors. And so there's a unique other pentachoron that it meets in this 3-phase. Yeah? So actually the 4 simplices or pentachoron, they come naturally in these pairs. Yeah? Always 2. So there's an opposite guy here that also just has a isolated yellow vertex. So let's put it here. And yeah, meets it like so. Yeah, so for each guy there's this. And so on these pairs then you can actually do a Pachner move, yeah, a bistellar 2-4 move. So on these pairs or on each pair of 4 simplices do 2, 4 bistellar move. Yeah. Okay, and so what you get when you do this? Well, you get now 4 pentachora, and each of them actually has an edge, yeah, connecting the yellow vertices. So let's draw them. Okay, so so now I need to let's see. So let's maybe do it like this: 0, 1. Here's 0, 1, 2. Then I have 1, 2, 3. Then I have 2, 3, 0. And then I have 1, 2, 3. Yeah. So then I've in turn always omitted 1. Okay, so it's this, that's this, and this, and I have many mistakes somewhere. So here I omit 3, then I omit 0, then I omit 1, then I omit 2. Okay. Oh, that's where I made a mistake. Okay. Okay. And so, I don't know whether there's a better way of drawing higher dimensional simplices. Okay. Yeah. So this is a move we've made. Yeah. So this is just a standard move on the triangulation. We'll take the union of these two to these 4. Yeah. Just as the familiar sort of move maybe on 3 simplices, just which is easier to draw, right? I mean, if you think about 2, 3 simplices meeting in a face, then what can you do? Well, you can sort of subdivide them by dropping down an edge here, yeah, and then you make it three simplices going around this edge. Yeah, so this is just the equivalent operation, but just in 4 dimensions. Okay, and so then you see that you haven't changed, right? I mean, you haven't changed the number of vertices. They're still the same. And the only thing you've done is actually, how have you changed the one skeleton? All you've just done is you've added edges. Yeah, you haven't taken any away. Okay, so if you now keep the partition as it was, this guy stays connected, this guy stays connected, and this here also becomes connected. Yeah, so this here now is also connected. Okay, so this means that we've achieved the first part. We've sort of created these partitions of vertices into, in this case, 3 colors: red, blue, and yellow. And now if you want to define a simplicial map of our manifold to 2 simplex, it's easy to do. Yeah? We just have the 3 partition sets and we send them to 3 vertices of a simplex. Okay, so can now define partition map from 4 to 2 simplex by just doing exactly this. Take the 2 simplex, just color its vertices blue, red, and yellow. Okay. And so this tells you what you need to do. Okay. And so what happens here is that if you look at pre-images of points, I claim that these are again actually cubes. Okay, so let's look at one of these. I mean, here we have now somewhat 2 different types of tetrahedra, but they kind of dual to each other. Yeah, so each tetrahedron, let's say tetrahedron, so Freudian slip, I guess. So this is each pentachoron here. It does have sort of a yellow edge, but then may either have a blue edge or a red edge. Yeah, so the isolated vertices are now actually blue or red. And I'll be very happy for them to alternate in this fashion. Okay, so let's take one of these guys and just look at what happens. So if I take one, let's say 2 red, 1 blue, and 2 yellow, and see how this maps here. There's some edges missing, right? Okay, so then what's the preimage? What's the dimension of a preimage? Well, here it's just a vertex, so dimension is 0. Yeah. Here the preimage of this guy is just a 1 cube. Yeah, it's just a 1 cube. The preimage of this guy is just a 1 cube. Yeah. Okay. So what's the preimage of say a point along here, along this edge? Sorry?
It's like 3 here. It's a square.
Yeah, it's a square.
Okay.
Yeah, because this here, of course, it pulls back to this tetrahedron, and we meet it in the square that's in the tetrahedron. Yeah, so this is actually 2 cubes, and that's true for everyone along here. Everyone along here, the preimage is a 2 cube. Yeah. Okay, and then what's the preimage of a point along here?
Interval.
Yeah, it's just because if you look at what's spanned by blue and yellow, is just this triangle, and so the preimage of this one is just an arc like this here. Yeah, so this is a 1 cube. And so similarly here, it's just a 1 cube. Yeah, so you see along these edges, the preimages are 1 cubes, and here it's a 2 cube. Yeah. Okay. And what's the preimage actually of a point, sort of inside? Is it? Let's see. So what do you actually see here, right? And you need to now think about where do you actually get say extremal points, right? Extremal points you get from. So you look at faces where you have all 3 colors. Yeah. Yeah. So if you have a square with all 3 colors, then you meet in a point like this square here, right? You meet it in a point. Yeah. And then if you think about sort of what happens when you have 2 such squares, so let's draw it as a sort of tetrahedron, right? And what happens when you have a tetrahedron that looks like this here? Okay, so this now means you meet this face here in a point, you meet this face here in a point, which means you meet this tetrahedron in this arc. Yeah, that's what you pull back, right? You pull back this arc here from just, right? I mean, all that happens under this map is you just flatten this tetrahedron onto this face. Yeah, so if you pull it back, you get this arc here. Yeah, okay. Yeah, and so if you follow this around, well, how many do you have of this type of tetrahedron, right? And you have one tetrahedron that has not 3 colors, yeah, and all other tetrahedra have 3 colors. Yeah, so that's the other 4. So you get these 4 arcs, and you get 4 vertices, so you have a square. Yeah? Yeah, so the preimage of this point here is also a square. Right? Yeah. And so you have this square here, and now you can go even further, just because it's so much fun. Right? So that's true for any point here, right? Any point here pulls back to a square. Yeah? So this means that if you look at, say, this cube here, because I like to focus on the cubical structure of this simplex, right? This thing here pulls back to actually the boundary square that you have times an interval this here. Yeah, it pulls back to this here. Yeah. Once, if you look at something like this bit here, let's make this here yellow. So this yellow guy pulls back to what? I mean, here you see these squares, and then they collapse to something one-dimensional. Yeah. Yeah. So this pulls back to the square, and then it collapses down to this one-dimensional thing here. Yeah? That's the preimage of that thing. Okay? Yeah. Okay. And so now we're kind of ready to do what we want to do. Yeah. So which is good. So if you think about the preimage of this point here, preimage of this point is a graph. Yeah. So we established that this is a graph in here. If you now think about sort of this cube here, then you see under this map, this is just a regular neighborhood of this graph in M4. And because a regular neighborhood of a graph, then we know that this is a one-handlebody. Yeah. Okay. So this means that each of these kind of top-dimensional cubes pulls back to a one-handlebody. so this is kind of the first thing. So each, say, dual 2 cube in delta 2. And so with this I mean something like this here, yeah? Pulls back to regular neighborhood of connected graph. In M4, therefore it is a, I guess, 4-dimensional one-handed body. Okay, and the pre-images they meet. So that's good. So we have the first thing, right? So we have this. We have 3 handlebodies, and E is equivalent to standard 4-dimensional one-handlebodies. If we look at the interiors, by construction, they're disjoint, yeah? And also M is the union of these by construction. So we're done with this here as well, okay? So now we need to check that the pairwise intersection is a standard 3-dimensional one-handled body, okay? So if you take the pairwise intersection, so that's really the pre-image of one of these guys here, yeah? This pre-image of something like this here, yeah? Okay. So now we're in a pesky situation. So here we computed the what we get when we sort of look back, right? We see either things like this or we see things like this, yeah? And what you also see is that here actually, where does the 2 come from? The 2 comes from having an edge with the same color here and an edge with the same color here, yeah? That's where the 2 cubes come from, okay? So really then the 2 cubes we only get actually from pulling back things that involve the yellow guy, yeah? Because this thing here, in every tetrahedron, there's no, yeah? There's no edge that's red and edge that's blue, because all our pentachora look like this here, yeah? Okay. So the other thing that we notice here is that actually here, of course, here's a nice collapse here. So here's a collapse from this to this, right? You can just sort of collapse this here down. And because we sort of built everything this nice way using these simplicial maps, this actually lifts to a collapse. Yeah. So the intersection. So the intersection of 2 of these guys. So H, say I intersect HJ. Yeah. So this is really the pre-image. Have we given this map a name? So all my maps are always called phi, regardless of what they are. So I have, so this is really phi inverse of one of these 1 cubes. Yeah, and this actually collapses down to phi inverse of a. So this is. Maybe the dual 1 cube intersect boundary of the trisemplex. Yeah? Or a midpoint, yeah? Very center of an edge. Okay. And so because it collapses down to this, so if this is really just the, say, if the dual 1 cube is now actually dual 1 cube on the blue-red edge, then you know it's a one-handed body, yeah? Because it has a one-dimensional spine, okay? So we really need to worry about the other guy. So case 1 is when I look at this one here. So the pre-image of this union of all simplices, and we get a three-dimensional one-handle body. Okay, so case 2 is the other case, and the cases are symmetric, so let's just pick one of them. Let's say you look at this here, yeah? So then the pre-image is a union oh, and here shouldn't have said one simplicity, let's call them one cubes. That's easier, union of one cubes and two cubes. Okay? And so how does this happen, right? It happens because in some tetrahedra we get these two cubes here. In some tetrahedra we get these one cubes here. Yeah? But how do they fit together? So if we look at this around one of these yellow edges, yeah, the way they fit together is actually to alternate. So what you see is actually a picture like this. You see one of these guys. This is maybe the best way to draw this picture. So let's say you have one of these guys. Yeah. And then it's followed by one of these guys. And then it's followed by one of these guys. And then it's followed by, whoops, one of these guys. And so this here is your spine. This is this kind of thing that we're collapsing to. Yeah? So here we've taken this collapse here. Inside our manifold is this collapse here. You have this three-dimensional object here. The annulus around here, the annulus boundary around here, that's your triple intersection, H0 intersect H1 intersect H2, yeah? Which we've already established is a surface. And I haven't written that argument down, but we made this analysis of how the squares meet. Yeah? So this is this. So this here collapses, of course. It collapses onto this here. And then you're in the lucky situation that here you have a free edge and you can collapse the square. Yeah? You can just collapse the square from this vertex, from this edge onto, say, the union of the other three edges. Yeah? Which means that you get a one-dimensional spine as well. Yeah? So that just comes out of this cubical structure then. Yeah? And so and can be collapsed, and there are, so and each 2 cube has 2 free faces from which it can be collapsed. Okay. And so this means we get a one-handed body in this case as well. Okay, so this is this. And then I said 4. We basically have discussed. I mean, here you can actually very nicely see how it works, right? And if you think about the surface, the triple intersection is made up out of these squares, yeah? And each square meets. How does it meet the faces of the four simplices? So see, it doesn't meet these faces here that have 3 distinct colors. It only meets the faces that have, it only meets sort of the 3-dimensional faces that have 3 different colors. And each of those it meets in exactly one arc here. So if you think about your 4 simplex, it meets another 4 simplex. And if the surface, if the square has an edge there, then from the other one you also get an edge. And so you pair any 2 sides. Yeah? And now we're just lucky that because if you take a bunch of polygons and you just identify edges, yeah, in pairs, you get a surface, okay? And the other thing you can actually check is that from this construction here, that actually the degree around the vertex is again at least 4, which means you get a non-positive cubing on the triple intersection from this here. So that's sort of an additional thing. We have this here plus, yeah, with the additional property, if you like, that you get this non-positively curved cubing on this thing here. Okay, and the other thing that we have as additional information here is that all of these handlebodies, all of these intersections come naturally with cubings, yeah, that have the same dimension. And here it's collapsing right onto a union of 1 cubes. Okay, but again in dimension 4, some things were easier than they are in the higher dimensions, and so that's where maybe some of the issues are. Okay, so I think I'm spent, and I've done this in some detail because I want to be a little bit more sloppy maybe in higher dimensions and just point out where the technical issues are and how you overcome them, and then talk a little bit more about more sort of open problems and other things. Anyway.
Questions? Is this the original definition given by Kirby and Gay?
No, so it's not. That's why I pointed out.
Combinatorial kind of argument.
Oh, so
they did different, right?
yeah. So Kirby and yeah, I should have said this. So Kirby and Gay, they give 2 existence proofs in their paper. And so one existence proof is via their Morse 2 functions. So you think about Morse functions to simplices, yeah. And so and that's, you could say it's sort of trying to be analogous to the 3-dimensional proof existence of Hegart's proof using Morse functions. But there are of course a lot of complications there in higher dimensions that they have to overcome. So they use Morse 2 functions, and then they give a second proof, and that's sort of motivated by the observation that when you look at these, I said you have these kind of trisection diagrams where you take the surface and you actually draw the attaching curves for all 3 handlebodies on it. Yeah. So that's very similar to things that happen in Hegar-Fleur homology. And so based on this observation, they also give a proof just using Handel decompositions and Handel slides. Yeah. Mm-hmm. Yeah. And so this is then, and then Dave basically asked us whether we thought there might be a proof using triangulations, and that's how we came to then, I mean, do this, but then also sort of generalize this to higher dimensions, because the triangulations proof sort of generalizes quite nicely to higher dimensions. Yeah.
So for manifold case, so does this trisection captures like smooth structures, for example, and so on?
I mean, so if you took something like the invariant that I talked about, right? And that would then be, it's an invariant of the PL structure or the smooth structure. Yeah. So you say what's the minimal genus trisection? Yeah. Of say the of a 4 sphere. I mean, now if you found a 4 sphere, yeah, that doesn't have minimal trisection genus everything 0, yeah, then you would have a 4 sphere with a different smooth structure, which I guess you don't expect. Yeah. But yeah, I mean it's an invariant of the PL structure, but we don't know whether it's a complete invariant of the PL structure. Well, yeah. I mean, in this case, PL structure, smooth structure is equivalent. Mm-hmm.
Other questions? Okay, thanks for speaking.